Hello and welcome back to MET 421. So just a quick recap to what we have talked about last time. We've discussed the three modes of heat transfer: conduction, convection, and radiation. Conduction, it's the heat transfer through solids. For example, if you have the inner air of this furnace or heater at a given temperature, the outer surface at a different temperature. So how much heat will be transferred through the walls if it has a specific thickness, and this is Tn, or in general, let's say this one here, T inside, and this side temperature, the outer, it's T out, not the air temperature. Once we start talking about the air, that becomes convective heat transfer. So the convective heat transfer, if this surface is at a temperature T1, for example, and the air right here is at a temperature T2, and there's air in between the two, so the heat transfer rate Q, it's equal to H, the heat transfer coefficient H, which is kind of like the conductance, how much it represents a resistance against the transfer, but it's 1 over the resistance. So it's the conductance, the conductivity of the heat, but this is through the air. As we've seen in conductive or conduction heat transfer, it has a factor called K, which is the thermal conductivity of the material. Here we're talking mainly about air, so the air convective heat transfer coefficient H. Then A is the cross-sectional, the area that we are considering here, and then we have the temperature difference T1 minus T2. If we do English units, then the area would be in foot square. If in SI, let's say it's going to be in meter square, and then we'll have the Q right here will be, if we take the English units, BTU per hour for Q, delta T Fahrenheit, the cross-sectional area foot square, that leaves BTU per hour foot square Fahrenheit for the convective heat transfer coefficient. For conduction, we use Fourier's law of heating for conduction. So K is the thermal conductivity, A, again, it's the cross-sectional area. So if you have a thickness, a wall, so this into the wall, that would be the cross-sectional area, A, and then delta T over delta X. So delta X represents the thickness, which you can use as T here. So this equation can be as K times the cross-sectional area delta T over T. So the temperature difference between the two, T1 and T2, divided by the thickness. Now, since we write here delta, that's usually going to be T2 minus T1. We know that heat transfer goes from the high to the low temperature region. Then this delta T is going to be negative, so we're gonna always be looking into the heat loss, and that's why we add a negative sign right here. The same we can do for unit-wise. This will be in BTU per hour. This one, degree Fahrenheit. Here we have inch or feet. this will be foot square. So if you keep this in inch, you don't cancel these two. You're gonna have K as BTU inch per hour foot square Fahrenheit. Some resources or references we have this, because in most cases you're gonna have the thickness reported in inches. That's one. Two, it's easier to look into the difference between this value K and the H. It's almost the same, this part, except now we have inch here for K, and that's because we have delta X, delta T divided by delta X, so you're gonna have an additional distance. If you decide to use T in feet, then you're gonna have K given in BTU per hour feet degree Fahrenheit, so it's not foot square. And also we'll have radiation. We're not going to go over that again. We have the equation, but in general, if you have all three modes and you don't want to do the three separate, we use what we call the overall heat transfer coefficient U. So then the heat transfer rate Q becomes equal to UA times delta T. The arguments that we did for H, they apply here. So U is the conductance rate through the material, or for the system, because now U can have the three: conduction, heat, and convection. Now how we determine that, we'll see in the coming slides, and then we'll go back to this equation. So we've discussed the concept of thermal resistance. We said there's an analogy between heat transfer and electric circuit, where Q, the heat transfer rate, Q is, there's some analogy with the current I through this. There is the temperature difference, or we have heat transfer because you have temperature difference, whereas here you have, if you want, V in, V out, or in general you have voltage difference. So because of this voltage difference, you're going to have a current going through this wire. The same goes here. You have temperature difference between the two surfaces, so that's why you're going to have heat transfer rate. Now, what controls this current I, the flow of the current I, or the flow of the heat transfer rate, it's the same. So I is determined by the value of delta V and the resistance R of inside the medium that it's going through. The same goes with Q. So Q, we want to define now Q, the current or the heat transfer rate, as delta T. So delta V, delta T, we will formulate some equations that are analogous, or where they share some analogy with this equation down here. So Q is the same as I, delta V as delta T. Now whatever is left inside my equation, that represents what we call the thermal resistance, and that's why we have RTH. And then let's remove now the voltages, because that's my thermal resistance circuit now. Okay, so you have here a thermal resistance, temperature difference, and Q, it flows through that. And that's what we need to find. Now Q, we need to find that heat transfer rate. Delta T, we know that there's temperature difference, so the question would be, what's that thermal resistance R? Now if you have conduction, as in this case, you'll have to compare this equation to the previous definition right here. So we can see 1 over R, so Q, it's equal to both, delta T cancels, and that leaves K A over delta X equal to 1 over R thermal, that's for conduction. Or if you want, R conduction is equal to delta X over Ka, or if you want, it's T, the thickness, divided by the thermal conductivity times the area. The same goes for convection. In convection we said, if you go back to this equation, Q equals HA delta T we want to write this as delta T over R thermal, but that's for convection. So the same way you're going to compare both, so delta T cancels with delta T, then HA equals to 1 over R convection, thermal or thermal convection, or R thermal, the thermal resistance for convection case, is 1 divided by the heat transfer coefficient H multiplied by the area. Okay? That becomes really helpful when you have a sandwich of material, like in walls. You have the blocks and then you have plaster material, you might have insulation, you might have additional board here and there, so we don't want to calculate Q over and over. So there's that concept where we said this determines now couple electric resistances. So you have V1, the first resistance, second, third, etc. So if they are in series, then this is R1, R2, R3, R4. There's a current I that passes through that. Okay, so R total is equal to the summation of all the smaller resistances I equals 1 to whatever number you have, or R1 plus R2 in this case, plus R3 plus R4, etc. So, and we'll go into the parallel just in a minute in the next slide. So if you have these three materials, A, B, and C, they have the same, they share the same cross section, so we're not considering different cross sections. So we have now the same as the current here flows through all of them. Q will be going in this direction because T1 is here and T4 is higher, or in general you have indoor and outdoor. We'll go to there in just a minute for the convection, but let's look into only conduction. So we know that Q is traveling in this direction from 1 to 4. Now we know that our conduction is the thermal is T over Ka. Now if the thickness you could have just some La plus Lb plus Lc if it was the same material, but the material is different then because the cross-sectional area is the same. So if K is different because you have different material, then you're going to have different thermal resistances, one for A, one for B, and one for C. Each one is defined as thickness. We define the thickness as L in this case. So it's L sub A divided by the thermal conductivity of the material multiplied by the area. Okay. Then we repeat that for B and C, and now you have all the thermal resistances for A, one for B, and one for C. We'll also do one for the indoor Ri, which is, remember the convection, it was 1 over h, and the one for the outdoor, which is 1 over excuse me, 1 over HO times the area. Now, because Q is constant through the 3, it flows like that at a constant rate, so it's then equal, similar to the current here. I is this delta V divided by the corresponding resistance. So the same goes with the temperature and the thermal resistance. So you can say here T1, it's Q equal to T1 minus T2. So we're looking across A, that's divided by RA. That's equal to T2 minus T3, so we're looking across material B, so that's RB, and so on. You can do it for C. Also, you can say, if you want, T1 minus T4 divided by R total, or RA plus RB plus RC, that's what I called here R, the total resistance. You can do any combination, and Q is still the same. It's equal also to, if you want, T1 minus T3 divided by, now we took from 1 to 3, so it's divided by the resistance for A plus resistance for B. This is really helpful when you want to determine the intermediate surface temperatures. So you might have two temperatures across, you have all the resistances, so you find Q, then that Q is equal to any individual or combined temperature and resistances. So you have the resistances, then you can find the individual intermediate or in between temperatures. So this is the case for series connection. You simply add the resistances as we've done in electric circuit. So RA, RB, RC. Now when you have parallel, the concept is still the same. So in this case, B and C, so A and D, they're in series, so you have one here until we reach here, and then still. Here, we're gonna skip this, come to here, and then we go from here to here. Now what happens here, it's an easy concept to determine whether they are parallel or not. Just look into the current, which is the flow rate, or the heat transfer rate. If QX splits, whether equally or not, as long as it's not the same, once it splits, that's when you know that it's going to be parallel connection. For example here, that's Q, it keeps going as Q, there's only one way. So it keeps going in this direction, so this is a series connection, and our total is simply the summation of all individual resistances. When you have parallel, Q is coming in this direction, and then it's gonna split up and down, so you have Q1 and Q2. So you would say B and C are parallel. So now you have one resistance here and another one here, and then they meet up and flow through D. Look what happens back. Q1 will add with Q2, then it's going to give you Q. So now you have a thermal resistance here, two right here, two thermal resistances, and then you have the third one, that's for RD, this is RB, RC, and RA, the resistance for material A. That's T1 and T2. So if you want, this will be, for example, A, here you have B and C and D. So it's very similar, except now we have B and C, those two, they are in parallel, and we apply the concept of parallel resistances. So 1 over the total for B and C, I'm gonna call it B and C in this case, it's equal to 1 over the resistance for B plus 1 over the resistance for C, and then we can flip it. I'm not gonna take a direct rule for flipping because you might have 3 or 4 materials, so you will always use the inverse. So 1 over R equals to all the inverse of the resistance of all the individual materials, and then you can work it out. If you have some numbers, plug it and find the number directly and then take the inverse. So this will reduce to RA, still there, RBC, and RD, R sub D. This will be now T2 and T1. So now if you look, that's Q, that was going here. And then when it's split, it's still Q, because now we combine those two together, and then here Q. So now those three are in series, so our total is RA plus RBC plus RD, where RBC we can find it from here. The easy way is simply just keep it like this. First, take a common value there, and then RC plus RB. Then RBC, R sub BC will be equal to RB times RC divided by, I know there are like a couple rules which you can use directly for the parallel, but let's just keep it simple just in case some of you're not very like professional or familiar with the concept of electric circuits and resistances. So now, if you have the convection, then 1 over H N times the area, 1 over H O times the area, you have all that. So I can then have a total resistance for the wall and the air surrounding. So it's RA, RB, RC. Those are the three in series, and then you have, even if you have multiple walls, you're gonna do that first, add it, and then you add Rn and R out, where these are simply the convective resistances indoor and outdoor. Okay, so my equation, the last equation becomes, the final equation I mean, delta T over R total, which can have both conduction and convection inside it. And that's what we use for my definition when we say UA delta T. So U, as you see here, UA is equal 1 over the total thermal resistance. So if the thermal resistance increases, so you have more resistance, then U decreases, right? So U is actually 1 over RA. If you want, A is just a constant. So as the resistance increases, then U decreases, or as R decreases, then U is going to increase. What that means, as the resistance of the wall or the material increases, then you have less or lower heat transfer rate. And it's the same because R is down here, so if R increases, this will make Q decrease, or if U increases, sorry, we said R increase, then if U decreases, then Q is going to decrease as well. Or the opposite. You can just think of U as a conductance, so the ability to conduct. So as the ability to conduct is less, then the heat transfer rate is less, it's going to reduce. Or if the resistance increase, that will make the conductance less and the heat transfer rate becomes smaller. Now why I'm discussing these, because we have tabulated values for different materials for the U, for the overall heat transfer coefficient. Also, there is another definition, which is the thermal resistance per unit area, R double prime. That's actually U equals to 1 over R double prime like thermal resistance per unit area. So if you compare this to the other equation, R double prime becomes equal to R times A. Or if you want, R as R double prime divided by A. Now there's a big misconception or a big mistake that students make. When you add the thermal resistances, don't add U. So if you have the U value tabulated, don't use the U to add here. No, we always add, because those two, as you see, they're inversely proportional, U and R. If you change the thickness, don't just simply change the U. You can't directly change U and thickness. U is inversely proportional to the thickness, and we'll see that in the tables. But you do need to convert U, or do the inverse of U, multiply it by the area or divide, or you can just simply, if the area is constant, just simply keep it as resistance flux or thermal resistance per unit area. You add the thermal resistance and then you convert back to the U value if you need to. And that's what I have here for you in example 1. So you have the 3, so you have a block wall, you have 2 gypsum or cement plaster, and also it's cement plaster inside and outside. You have inside film and outside film. So you're gonna have this, but notice that we're only reporting the flux, so it's divided by or multiplied, if you want, by the area. That's R times A. That's because it's equal to 1 over A, and then 1 over HI plus delta 1 over K1 plus delta 2 over K2 plus delta 3. So delta in this case is the thickness as given here, thickness of each layer, plus 1 over HO. This right here is R double prime, the heat flux, and the total is R, so that becomes R double prime equals to R times A. Let's look into more numerical examples. So we have a double glass window with an area A which is 30 times 50 inch. The thickness of each pan is 0.2 inch. So T glass here is 0.2, and right here is also 0.2 inch. And the air gap, it has a thickness TA equals to 0.6 inch. It separates the indoor air from the outdoor, so the outdoor is at 20 degrees Fahrenheit, the room temperature is at 71 Fahrenheit. The thermal conductivity of the glass, K glass, is 8, and that for the air gap is 0.3. So those are the thermal conductivity. The inner room, HR right here is 0.8 BTU per hour, foot square Fahrenheit, and H outdoor is 6 BTU per hour Fahrenheit, foot square. Find the heat loss through the window. Now that's at 71, that's 20. So first you need to put your Q, it's going in this direction. You can draw your thermal resistance. So we have We have first the 3 materials. We have glass and glass right here. So the thermal resistance, remember, for conduction is the thickness by thermal conductivity times A. So it's going to be T glass over K glass times A. T glass, K glass, A. This is here. You start right here, T1. So you have the first one, glass, air, glass. You have T1, T4. Okay, everything is shifted. This is T2, T3, T4, and T infinite. It's behind this. 6. Let's clean it. And then the outdoor 1 over HA and the indoor 1 over H room times the area. We need to find Q, so we have only the room temperature and we have the outdoor temperature. We don't have the intermediate temperature, so we'll have to take this section from here to here. So we'll have to find the total thermal resistances. So the area is constant for the wall. It's 50 times 30. That's 1500. We'll convert that into foot square, so 10.42. And then we're gonna apply this to each individual item right there. So this will be 0.12, 0.016, 0.00 for the glass. This will be for the air. This is the outdoor air, and this is the room. So we're gonna add all the thermal resistances together until we get this total, and then we're gonna use delta T over R. Delta T, as I've said, the room minus the infinite, which is, as I've mentioned before, it's equal to T1 minus T4. So T1, or here, T1 minus T4 divided by those 3. But we don't have those 2 temperatures, but in case like we want to find the inner and outer glass temperatures, T1 and T4. So first we're going to use this to evaluate Q. Whatever value we get here, we're going to use it in this equation, or if you want even the individual T2 and T3, which would be part of the homework that I'll be assigning for you, like find the individual or the intermediate temperatures. So you're going to define, for example, in this case it's not T2 because you don't have any of those, T2 or T3. So you'll have to use room temperature TR, because this also equal to T room minus T2 divided by R for the room plus R glass. If you add here T3, then you're going to add R air and so on. So 71 minus 20 divided by that total resistance, and that's gonna be equal to, this is right here, so we'll have 334.6 BTU per hour. That's the heat transfer. Now we're gonna use that T room minus T1 from here to here, so that's only we have R for the air, or inside the room. So it would be 71 minus T1 divided by 0.12, because that's the air for the room. It's 0.12. So we can get then T1 from the equation. We also need to find what T4. I don't want to use the from the room side, because then you will have T room minus T4 divided by, let's count, we're going from here all the way to here. So from here to here, we need to find this one. That's going to be divided by R room plus R glass plus R the gap, the air gap, plus R glass. So you'll have all these. If you want it to be like a shorter way, then you could have simply said not even this one, the last one, T4. So I'm gonna only consider between here and here, T infinite, T4, so that's this section right here. So T4 minus T infinite or T outdoor, divide only by the outdoor resistance. So whatever subscripts you use here or those two terminal temperatures, you're going to divide by the included resistances, and it should give you almost the same answer as you see here. Okay, next. So now I want to take you through the tables where we can actually get some material properties. So as you've noticed, so far I've been giving you like this example, or we've done a little work in the previous chapters where you will have the thermal conductivity, but here we need to have more specific details about, because we'll be talking about the thermal conductivity or heat loss and heat gain through buildings. So we need to know the thermal conductivity, the conductance or the U value for walls, for roofs, for windows, for doors, and that's what you will find in Appendix C. If you go to that appendix, we have the, for example, as we see here, you have the building board, so you have different materials like gypsum or plasterboard, plywood. And then for these values, where you have what we call the conductance, which, as I mentioned, this is the U value right here. Those will have specific thicknesses. So it's equal to 16.5 only for that thickness. If the thickness changes, then you're gonna have, as you see here, if the thickness changes, then we're gonna have to reevaluate the U value. Okay, we don't do that because it's the inverse, so many of you will make mistake. For example, if the thickness goes to 0.5, what I'm talking about here, the first one, if T is 0.5 inch, then the U value, if you can see this equation that it's 1 over R, so as T increases, U has to decrease. You can actually say U is going to be 8.25. It's half. Sorry. Yeah, we doubled. It's just coincidence that this one's that. We doubled this, so you have to divide. But when you have multiple walls, especially with parallel, it becomes more confusing. So simply just convert that into resistance. So the resistance, it's T over K. If T is doubled, or the resistance per unit area, or Ka. If T is doubled, then R will be doubled. U is 1 over R, therefore U will be half. Again, it's simple for one, but once you have a sandwich of material, like multiple materials together, you're gonna have different, you'll have some confusion. Excuse me. You'll have some confusion and will make a mistake. The other type, if you don't have the U, you're going to have the K value listed directly. So for K value, you notice you don't have thickness here. The thickness will be given for you. For example, if you have a thickness this much for plywood, then you're going to come to here and use the K value. Be careful that this K value is, as I've mentioned, it's reported as BTU inch. So the thickness here needs to be in inches. when you substitute the value to find R, it's T over KA. Just be careful, make sure that you substitute T in inches to match to have the right units. Okay. You do have English and SI units for both. So table, let's take a quick look there. So if you go to table, appendix C, there's a very long, it's not very long, but it's still long, because I'm saying it's not very because you have other references for very detailed materials. This is from ASHRAE, American Society for Heating, Refrigeration and Air Conditioning Engineers, handbook, sorry. So first we start with table C1. I called it C1, it's table 5. We're gonna neglect those, as I mentioned before. We're gonna use the red for our reference. So first you have the building board, such as like cement board, gypsum or plaster board, hardboard. What do you have? You have, as I mentioned, if you have the U value, you're gonna see that the thickness reported. You have also some other values such as the specific heat or the density, but those are the two main things that we need. If you have this thickness and the thickness is different, like sometimes you don't have a couple ones, like in the plywood case, you only have, like here, only quarter inch, it has that U value. Well, you have now in your example, for example, I'm just saying, like half inch thickness. You need to find that U value, don't directly use the 16.5. You'll be looking for the material that you have, like you have building membrane, vapor or vapor seals. Usually we take 0 for these because the conductivity is so high, so it has a resistance like very small. So the resistance, we take it negligible, it's going to be 0. We'll see some numbers. If you have floorings, if you have like insulation, different insulation thicknesses. So what you have there, you have the U value or the conductance C, okay, and that's because the thickness is right here, like 3.5, 5.5, 6 to 7. So the thickness they're taking like average for those ranges, or exactly 5.5. That's why you have the U value or the conductance. Then you have boards and slabs. You can go through it. You have metals. You have roofings. So roof with shingles or built-in roofing, for example. We'll do an example here, or maybe the homework. It's 0.375. The roofing will be different for you. That's equal to 3. So if the roofing is different, make sure you change that value. And then we have bricks. You have concrete blocks with 3 different weights: normal, lightweight, and same with this, filled with like some other stuff, filled core, 8-inch, etc. has those U values. If the U value is given, or the R value, or even the conductivity, it's given as a range, we're gonna take the average of the numbers. Let's keep moving. Excuse me. Those are the same, except they are sorry, I meant for table C2. Here we have more material. C2, it's the same, except it's for SI. So you're gonna see the same material, but with millimeter and joules, kilograms. In this table C3, that's where you're gonna get your H value. So the H, the convective heat transfer coefficient, you have indoor and outdoor. That's indoor, it's still air, and the outdoor, it's the moving air. The indoor air, it depends only on the temperature, the indoor temperature, so we don't have summer and winter. For moving air, the outdoor, you have winter and summer values. So these are for winter, and these here are for summer. Okay. The values are, so you have H in BTU, so in English, and SI, or if you want the resistance directly, they give that to you. So 6 for outdoor in winter and 4 in summer. That's BTU per hour foot square degree Fahrenheit. Now for the indoor, it depends also on the wall. If the heat transfer rate is, for example, it's horizontal, so sorry, the surface is horizontal. So in this case, if we have a vertical wall, you have a vertical wall, then the heat transfer, the direction of the heat transfer is horizontal. So you're going this way. Then H here, it depends on the emissivity of this surface. H indoor can be found from, for example, here, if the emissivity is 0.9, 0.74, if the emissivity is 0.2, and so on. If you have a roof, for example, just simply a horizontal roof, then the heat transfer rate will be vertical. So if the surface is horizontal, this will be upward, and the value will be right here for the 3 emissivities. If you have an attic and it's inclined, they only give you for 45 degree. Q is going in this direction. Okay, so that's where you go. You do this, and that's when it's in winter, so you're losing heat. Because this case, whether it's going up or down, it's still the same, but because it's horizontal with 0. Now if it's yeah, that's if you're losing. Now if you have a partition, we'll reach to that, but if it's inclined and the direction is in this direction, so H will be 1.6 and so on. If it's sloping 45 and it's going downwards like that, in most cases if it's an attic like this, so it's moving downwards in summer, so H will be different for the indoor. It would be 1.32 instead of 1.6 and so on. And I'm only doing English. We can read the SI. And then also if you have this surface, so these two are not equal, right? So you're losing the heat in this direction, not up, then the H indoor will be slightly different than the other case. This is table C2. We've covered this, so I'll just skip it. This is example 3, although it should be before table, but we can do it. We have T1, T2, and T3. What you notice is they have different areas. They are in series, but they have different areas. So you're gonna have T1 here and T2. So this will be T1, the thickness, divided by K1, A1, and this will be T2 divided by K2, A2. Okay. So this, I called it R1D and RSP. You're gonna add up to have your total resistance, and then you'll have T1 minus T3 divided by the total resistance. Okay, we've covered the U value, so now we come to the individual U values. For Windows, you have, let's go back to the PDF. So table C3 has that for you. And then we go for Windows, you'll go to table C5. The glazing, if you have first, so these are the U values right here. That's BTU per hour foot square Fahrenheit, so that's it says U factor or U value. Then before reading these numbers, you have to decide if it's single glazing with like different thicknesses, double glazing with some given emissivity, double glazing, triple, etc. Then if you're right here, then which value you need to read about the frame. If the frame is, it doesn't have frame, it's just glass, it's different between the center and the edge of the glass. If it's in the center, it's the same. Sometimes you might have different thicknesses between the edge and the center. So these values, you might see them different as you go to the double. You see here, only for single they are the same. So as you go down, you'll have different values between the center of the glass and the edge. If it has a frame, it's fixed, then it's just this column. You read from this column, and then if the frame is, like the different cases, aluminum with or without thermal break, so you have these values. Remember, that's the U value, it's not the resistance. And those are assumed to be in vertical installation. So if it's horizontal, you have to find the right reference. This is in SI, watt per meter square Kelvin. So we'll keep going. And then I need something for walls and insulation. Sorry, doors and insulation. Insulation for basement. So for doors, again, it's a table C8. The door, here's the door if it's wood or steel door. So first you have to find your thickness. If the thickness is the same, then you need to know more about the door itself, like solid core or hollow core. And then you read if it has a storm door or not. So no storm door. This value, it's the English, the one in between parentheses, it's in SI, and that's what it should be, more like parentheses rather than bracket here, but that's what it is. This is the English and that's the SI. If it's steel, then it's the same right here. If it's steel, we don't use metal storm door with that, except in this case. And then we go for basement. The basement, again, we will be looking into the U value. That's table C9. If I need to know like at what depth I'm looking to find Q, or the depth of the basement in general. So let's say we're at 5. If the basement is uninsulated, just concrete, then the U value will be here, 0.2, or this one in SI, so watt per meter square Kelvin. Okay. If it has some insulation, like R12.5, then the U value will be equal to 0.054 if the depth is 5 feet, and so on, like different depth and the thickness, and then you'll pick your U value. And the last one, heat loss through basement floors. If you have a floor, the floor of the basement, how do we determine Q? Again, if it's a different grade, like we only have, 5, it has to be at least 5, 6, or 7. So based on those, then what's the shortest width? If it's not square, we look only into the short width, and we match it with this here, and then read the U value. So if we're grade 6 and we have a room that's 20 by 30, then we're gonna be 20, and the grade is 6 feet below, so your U value will be 0.3. And that concludes the tables for this chapter, so we'll skip these here, because we have them, and we'll solve example 4, 5, 6, and 7. So what we have here, we have a wall that has dimensions of 20 by 8 feet. It has a door and a window. The wall has a U value of 0.07 given here, or if you want the SI, but we're going to do the English units. It contains a solid urethane foam core steel door, which has these dimensions, 80 by 30 by 32, these are in inches, and has a thickness of 1 3/4. Okay, so it's solid urethane foam door, steel door. So we go here, steel, 1 3/4, solid urethane foam core. Now is it, yeah, that's the only one that's solid fire. So we have this, so my U value will be 0.4. That's the door. Let's check the window. A double glass window that has 120 times 30. The window is metal sash with no thermal break. So let's go back to the window. It's double glazed with 1/2 inch and it's metal sash, sorry, with no thermal break, without a thermal break. So we're right here, 0.81. So we'll take that U value. So we assume that it's 1/2 inch, which is right here. That's why it took me a while, like before I say 0.81. Okay, what do we need to find? Assume parallel heat flow. So now if you have heat going this way, it's gonna split between the wall, the door, and the window before going in. Find the overall thermal resistance and overall heat transfer coefficient for the combination. Again, this is parallel, so don't do the U value, don't add the U value. That's why I said convert to resistance. So don't do 1 over U, 1 over U, 1 over U. Let's find the resistances. What's the relation between U and R? So U is 1 over R double prime, or R double prime is 1 over U, which is 1 over RA. So the door, it's 180 times 32, and then we're going to divide that by 144 to have the area, the same for the windows. Then the total wall area will be 20 times 8 minus those two. It should give you, so 160 minus 25 minus 1778. Yeah, it should give you 117 minus area of the door should give you 117.2 foot square. So they are now parallel, so 1 over R total for the all three. It's 1 over R for the wall, R for the window, and R for the door. We know that U is 1 over R. So then this becomes U times A from here. So UA total is U wall, area wall, plus U window, area of the window, plus U door, area door, and that's what we have. Yes, I just flipped the window and the door. So that's what we have here, and we can use it to find the total U value. So we'll just plug the numbers, 0.07 times 117 the wall, and then for the door, and that's 0.81 for the window, divide by the total combined area, which is simply 20 times 8, so that's 160. We're gonna get U equal to 0.222 BTU per hour foot square Fahrenheit. So that's the overall heat transfer coefficient. If we need to find R, we'll simply use this equation from here. So R is 1 over UA, so 1 over 0.222 times 160, that will give you 0.028. Okay. Example 5, we have a basement wall that extends 6 feet. Below grade is insulated with an R value of 12.5. The inside finish, so that's the insulation, or is that the wall? We have vapor seal, 1/2 inch, and we have 1/2 inch insulating board. We have plastic vapor seal, and then we have 1/4 plywood paneling. Compute the overall heat transfer coefficient for the wall. So first we need to find for the basement wall, which has an insulation of R 12.5. So we will have, we're doing English, the basement is 6 feet, we'll go to that table, or we can open, I think, yeah, it's in the PDF. Not sure if I have it next. No? Okay. Let's go here, go to table C9, so we're at 6 feet and 12.5, so that's 0.052. Okay, so that's 0.052 BTU per hour foot square. Then for the half-inch insulating board, let's see, what do we have here? Half-inch insulating board will go to table C1, and we'll see that. And then the plastic vapor seal, if you remember, I said we're gonna neglect those, but this turns out to be almost, it has a U value of 16.7. This turns out to be 0.55. I'll show you this one, but if you look into this, and then what do we have, the last one? 1/4 plywood paneling. It has a K value of 0.8. Once you compute the U value, you can compare it to 16.7. You'll see that this U value is really high, or since we'll be doing resistances, so the resistance will be much less. Let's go to table C1 to check on this, 0.55, and this one, 1/4 plywood paneling. So let's go to table C1, the first table. C2 is the SI. We have insulating board, half-inch. Okay, we're here. If you go down to the insulating material boards, okay, what's that? It's a wall. What's this one? Insulating material. Okay, roofs. Trying to find it for you. Oh, there it is. I couldn't see it. I passed it like 5 times. Okay, siding, because it's a wall, so it's not a roof. It's not. So insulating board with the only one that's available is 0.3. This has foil bagged, so we're gonna only use this. 0.375. It has a U value of 0.55, but that's only for this thickness. So let's take it, but before we go, let's find also for plywood paneling, which is 1/4 inch plywood. So you can directly use this because that's 1/4 and that's what we have, 3.2. Or you can take the K, 0.8, whatever thickness you can find it. Okay, so to write down these two numbers. Okay, so we said for 0.375 inch we have a U value of 0.55. This is 0.5 inch, half inch, so we have to adjust the U value right here, right? Oh, I didn't do it for you, okay. So the 0.375 has a value of, we can find the thermal resistance first. So R, let's see how much space I have. It's not that much, but so R double prime as 1/0.55, and that's equal to T over K. That's equal to 1.818. That's 4.375 inches. Now we've increased that into 0.5 inch, so if you divide this by that, you're gonna multiply this by 1.33. So this you need also to multiply by 1.33. You'll have 2.41, the new resistance. So the U value for half inch, it would be 1/2.41, so you'll get 0.414. Okay. That's because T and R, as I've mentioned, are directly proportional. Now we increased the thickness from 0.375 to half inch, so you're gonna multiply by the same factor to get your new thermal resistance, and then you take 1/inverse to get your new U value. For the plywood, so that's 0.414. The plywood paneling has a K value of 0.8, or I mentioned for 1/4 right here, U directly equal to 3.2. Let's check on that. So T is a quarter divided by 0.8, you get 0.3125, that's the thermal resistance. Take the inverse of that, 1/0.3125, you will get 3.2, so it was the reported value for that specific thing. So you see here you have 3.2 and 0.4 for these two, whereas this one is 16.7. That's why we said it's not significant. It's mainly to prevent moisture content transformation or transfer through it, but for heat it's not very effective. The U is very high or the resistance is very low. Now we'll find the final resistance for the finish only, so we're not considering the wall, so we're not considering this one yet. So 1 over this value for plus the vapor plus the plywood, that will be 2.73. That's the air finish. We'll add this resistance to the wall resistance, and that's what we call the basement wall resistance. So it's 2.73 or 72 plus 1 over the U value for the wall. That will give me 21.96. And now we're good to find the U value for the final one, which is just simply 1 over that value, and you will get 0.045 BTU per hour foot square. Now let's find the heat transfer rate through this combination. If the temperature is 70, the indoor temperature is 70 Fahrenheit, and I should say actually the soil here which we can say the outdoor temperature, or just wait a minute. Yes, the soil temperature at 35 Fahrenheit. This has an H of 1.3. We don't have anything here. We can assume, since this is 35 Fahrenheit, so we're in winter, so we can find okay, let's just forget about that. Let's assume that it's air, because that's how I solved it. I don't have H here, and I don't have the thermal conductivity for the soil. Let's assume it's outdoor air, so what's HO? We'll have to go to table C3, find the H in winter. You'll find that H is equal to 6. In summer, it's equal to 4. So this one is equal to 6 because it's winter time, because this lower than the indoor temperature. That H is 1.3. So to use that equation, because I only have those temperatures, I don't have the temperatures here, so we'll have to use between here, this whole thing, we already found it, and the indoor. This is 70 and this is 35 Fahrenheit. So we'll have to find the two resistances. We already found our total for the wall is this. With the indoor and outdoor, we're going to add 1 over H, 1 over H, the thermal conductivity for convection. We'll get a new resistance with the indoor and outdoor air. And then we're going to use, we can find U total, or you can directly use the equation, which is Q equals delta T over 22.884, and that's actually what we did here. Simply we took 1 over 224 and then we multiply it by the delta T. We don't have the area, so we're gonna do the heat flux, so it's the same exact answer. Whether you use this or you decide you want to use this. That's the heat flux because it's per unit area. Okay. Okay, let's see. Okay, I'm gonna skip this one. Let's see, group work. It's very similar to the one that we have just done, except it's different material. Let's go to the last one. You have a wall and a roof. The built-in roof has an area of 30 times 20 and a thickness of 2.5. The wall has a U value, it's given for you as 1.3, and area of 30 times 10. The outdoor conditions right here, we're only considering those two, so we're neglecting the other sides. It's at 100 degree Fahrenheit. The H is 4.5. That's summer because it's 100 Fahrenheit. And the indoor is 71 and 1.32. Find the heat transfer from the outdoor to the indoor in this case. Neglect the other walls. So if you notice, because you have two different thicknesses here and there in different areas, so those will be treated as pedal, kind of. You have T out here, you have the roof here, and then indoor, and then you have the wall, and then indoor. T in, T out. So if you play with this, twist it a little bit, it's gonna be something like this. This is our roof and R for the wall. So you can find each resistance, find the total, and then find the heat transfer rate, Q, because we have the two temperatures. Also we have, I forgot about these, the outdoor thermal resistance and the indoor thermal. Okay, so that's the first method that I'll be using. So the built-up roof has a value of I started with the wall. So the wall has a U value of 1.3. We already have that, it's given. So we can find the R per unit area. It's 1 over the U value, so it's 1.769. For the roof, you're gonna get 3 for a thickness of 0.375. That's something I mentioned for you in the table, so you can check that. However, that's for 0.375. Here you have 2.5 inch. So we're gonna first convert the, or find the thermal resistance that corresponds to this value, so it's 1/3. Now I have, for 0.375, I have 1/3 resistance. For 2.5, what is it equal to? Okay, so that makes, if you don't want to find the conversion factor, so it's 2.5 over 0.375 times 1/3. That gives me an R value of 2.22 and a U value of 0.45. And that's for the roof. We're gonna find the total resistances. So the total resistance, which is that for the roof. Since I'm talking about here total, you can keep it per unit area, but because the two areas are different, so you can't do that in this case. You will have to work with the total, which is R over A. So R is R times A. So R is actually R flux per unit area divided by the area. So 1/R, it's 1/R roof, so R double prime over A roof, R wall over A of the wall, A of the roof and wall. They're given here 30 times 10 and 30 times 20, and we already got the thermal resistances, 2.22 and 0.769. We'll plug these values. I'll find my 1/RT and then my final thermal resistance for the roof and the wall. So this the parallel connection. And then we're gonna add the two indoor and outdoors resistances. So 1/HA. Notice that the area, since it's around this, so it's this area and this area, so it's 300 plus 600, so I used 900 here. That's Rn. The same goes for the indoor, for the outdoor, and we're gonna get 2.47 times 10 to the negative 4. Here 8.42 times 10 to the negative 4, and I'm gonna make this as 15.15 or 14 times 10 to the negative 4, just to make all three the same. So now the total resistance, final total resistance, becomes equal to 15.15 plus 8.42 and 2.47 times 10 to the negative 4. That will be 26.3 times 10 to the negative 4. So we need to find now Q. That will be 100 minus 71 divided by that value, and we'll get 11,141 BTU per hour. Or you could find the U value, but there's no need for that. The other method, which is, you don't need to do it, but some people, just in case, oh, why I didn't do it that way, will simply find the individual Q. Q through this and Q through this one. So our roof, we've already discussed this. We found R for the roof equal to 2.22 divided by 600 if you want the total, because R double prime was 2.22 from the previous slide. So now R here up, it's this value, and this resistance. So you have three resistances, Tn and T out. So R out and Rn, we've already no, we didn't find them. Don't use the other values because the area was different. We used the total area. So we used area of the roof and area of the wall. So it would be just simply 2.22 over 600, then Hn, area of the roof, and H out, area of the roof. We'll find R through that wall. We'll divide 100 minus 71 by that value. We'll get 5,437. That's Q through the roof. Sometimes we need that to know exactly what's going through the roof, what's going through the wall. So we need to do this method. We'll do the same for the wall. we're gonna find, we already found the R value, it's 0.769. We'll divide this time by 300 because the area is different. And that will apply also for Rn and Rout. We're gonna use 300 and 300 right here and there for 1 over H, 1 over HA. We'll end up with this value for the total resistance through the wall, and then the temperature difference by that value will give you 4,975. If you add those two, you're gonna end up with 10,412. We got 11,000 watts. Yeah, there's a 600. There's maybe I did a mistake. I'll double check my values, but it shouldn't be that. Yeah, actually it does. The rounding of those numbers, I'm not sure if I did that, but I should have. The notes here, it's really big because it's 0.00. So let's say it's 5.33 times 10 to the negative 3. This negative 3 will become 1,000. So instead of dividing by 5.33, did I divide by 5.3 or 5.4? And the same goes here. Like, what's that rounding? And that's what I said right here. Okay, that concludes this chapter 6. We have homework 4 due next Tuesday, October 26th. And we'll do on Thursday, we'll be doing lab 4. We'll be meeting in the classroom, not in the lab. We'll discuss what we need to do, and then you can go in teams as posted on the on Brightspace, and we'll complete that lab. Okay, thank you.